Hi, my name is Gary Artini.
And my name is Akshata Karki.
We are from Holst Centre, part of the TNO, and from the Netherlands. And hereby we are presenting our developments for laser die transfer of micro components. Could be specifically micro LEDs as well, but for us actually it's like a black box. We developed a technology which deploys our proprietary release stack in combination with a low-cost laser source, which enables a selective transfer of components through the air, not in a vacuum, through the air in non-contact manner. And we are able to achieve precisions of 1 micron in lateral dimensions and under 1 degree.
How small is this stuff?
You have a varying sizes down to 10 by 10 microns. And the smallest what we showcase, but also we showcase here that we can have arbitrary shapes, like aspect ratios from 1 to aspect ratios of 5. And for all these dimensions we can achieve high selectivity. So we can transfer one die on demand without disturbing the neighbors, and to enable this at a very high density wafers, where edge-to-edge spacing can be between dies only a few microns.
It looks so cool and it's so precise, is it?
It is precise.
Yes.
So what could you do? Could you do displays with this?
Eventually, yeah. That's the idea behind it. But at this stage what we showcase is only transfer, but transfer is not good enough. Eventually to have a light coming from the micro LEDs you need to bond it. And typically majority of the cases that are showcased here are enabled by thermal compression bonding in contact. But what we are developing, we want to disrupt it a bit and showcase a flip chip bonding of the micro LEDs in combination with wet interconnects.
Because micro LED is doing all these different ways they want to transfer, right?
Yeah, that's right.
And this is another way?
This is another way. There are similar ways out there compared to what we do, but the disruptiveness what we bring is in combination with having it high throughput, having it precision, and doing it in a non-contact manner because it enables full color ones with the same technology and especially repair.
Repair?
Yeah, because it's what we do now. We have a mass transfer technology at first, right? You transfer many at once, but we always have faulty ones. People are solving it with redundancies, but if you would have a contact technology, you cannot do that because you have empty space. Well, many things are populated. You don't have any more flat empty space. Those are populated, so contact technology will not work. Then you have to have a separate technology for repair. And often this step is very time consuming and expensive. And now it's the same hardware, same selectivity done for mass transfer. So you select the vector file, you say, I want to transfer millions of these dies. And then there are some empty ones or some faulty ones, it's not a problem. I activate my laser and tell I want to transfer this extra die with the same hardware, with the same process.
So that means your yield is 100%?
That's what we ultimately is, but in combination with two processes, right? First mass transfer, and then detection of the faulty ones, and then repair.
So if this works, micro LED is going to be so cheap.
Well, micro LED display eventually will be cheap if micro LEDs are cheap, if the technology is mature, and then similar.
Yeah.
What do people ask here in the show?
What is specifically here?
Yeah, what did they ask you? Do you speak a lot with the display companies here, display people?
Yeah.
And they want to see if it's possible to put it in there?
Yeah, I think one of the things they ask is what is the distinguishing factor from the existing micro LED based technology out there. And so I think, as Gary explained, it's these things like high selectivity, being able to use a low-cost laser source, and high accuracy as well.
Yeah, because it's not that we are only ones who have sought to use a laser, right? And laser is intrinsic part already now in fabrication cycles out there, right? Because there is a lift-off, so laser is already used, but this is used typically for whole lift-off of everything, and then they do either using a laser trying to do selectively in contact, but then what do you do with the repair? That's out there, and then it's solved somehow differently with a very time-consuming process. Or there's also several parties that are doing regular similar laser type transfer, but the issue there, if you attempt to do it in non-contact, you have to be super gentle because a tiny micro LED is flying in the air in a large gap, for the die size, and achieving that accuracy is a challenge. So you have to have a process which is fast but also very gentle, and that's what our unique position is.
So there's a very precise laser.
No, there is a core of it. Laser is just a source, and you have to tune and select the right laser. But the core behind it is our release stack, which is a multi-physics process, and which enables a release of the die. So activating laser is activation. Then die is activated, is released fast, and flying in the air with not too much kinetics, so gentle. That enables to be precise.
Flying gently in the air is the ultimate dream of humanity.
You could say that, yeah.
And what are other applications? Because can you do stuff in all kinds of electronics?
Yeah, I think you can basically transfer any type of shape of micro components. So one application could be in photonics, for instance, where you can have varied aspect ratios.
Like a waveguides example.
Yeah, waveguides is an example of this. So any sort of transfer of micro components you can.
So you go into the optics.
Yeah,
not
you can
shape the optics,
yeah.
but the element that can be, for instance, for photonics, you have to stack indium phosphide on a silicon nitride example, and then this waveguide is odd-shaped, elongated stuff. And now there are challenges because the overlay accuracy of the transfer needs to be extremely good for optical coupling. That's already a challenge by itself. Another one is the waveguides are odd-shaped. So you have to transfer something odd-shaped and super accurately. That's a challenge. And what we showcase is that we can maintain accuracy even though we are transferring something very awkward, 1 to 5 or above the aspect ratios.
And it says here, component miniaturization. You're talking very small stuff.
Yeah. The key there is to transfer stuff that are commonly not possible with the pick and place, right?
Yeah.
That's a differentiator. And the microliths are already super tiny for pick and place, but there are many other components that are either awkward shape or still small enough, like a microlith, that are not able to be transferred in pick and place, and that's what we are showing.
All right. And any materials?
In principle, the release stack enables to be in activating the material with any backmetallization or surface. That's not an issue. The question is, there is a certain post-processing involved in our process afterwards, and compatibility with that device is something to be checked. But so far, with all semiconductor standard devices or microliths included, that's not an issue. But
and what does the machine look like?
So I think we have a prototype here of our working R&D tool, where you can't see it super clearly, but you have a laser source coming in through the top, and then an ability to align the donor and the receiver plates to have transfer with a fixed gap or a gap of your choice. Yeah.
Nice. All right. Cool. Do you think you're going to win the best of iZone?
Well, we are here just to showcase, not to win necessarily, but we'll be happy.
If you don't win, who's the best here?
Who deserved it, I would say. I will take it like that.
Okay.
Yeah.